Okay, we begin. Welcome to this talk about commercial AI. What is the situation in artificial intelligence today? What are the problems and what are the opportunities to be had in solving some of these major problems happening in the world of AI? So you've heard all the headline kind of news about all this amazing new technology, all these amazing startups, kind of unicorn, multi-billion-dollar AI startups. But what's behind it, and is everything fine? What's actually going on? Is actually something behind the scenes which isn't quite right, which, if we understood what it was, we could exploit for a market opportunity. We think that the world of AI isn't what it seems. There's actually really fundamental problems going on, which is not actually known to most people. So behind the hype, behind the headlines, are some real kind of problems with the way that AI works or doesn't work, rather. Okay, so start with, so the absolute godfather of AI in the world today is a guy called Geoffrey Hinton. Okay, he's the absolute #1 guy, and most of the top names studied under him as PhD students, etc. So now he says, Geoffrey Hinton says, no, he just changed his mind, but he kind of flips and flops. He kind of says this again and again over the years. He says basically, okay, so my view is to throw it all away and start again. I think the way we're doing computer vision is just wrong. It works better than anything else at present, but that doesn't mean it's right. Okay, so that sounds really strange, isn't it? I mean, surely this amazing AI technology, isn't it giving us all these amazing self-driving cars and all this amazing technology and all these multi-billion-dollar startups? Well, the problem is, okay, the problem is basically the main algorithm that's dominant in artificial intelligence today is called backpropagation. Okay, and backpropagation is behind most of the headline kind of AI you read about and hear about. Okay, so you might have heard buzzwords like transformers, convolutional neural nets, long short-term memory, generative adversarial networks. But behind all these kind of cutting-edge technologies is a technology that's really 70 years old. That backpropagation was really discovered, no, I should say 50 years old, was discovered in the 70s. Okay, so something really fundamentally wrong with this algorithm, and this algorithm is really driving the headline news, kind of groundbreaking so-called breakthroughs in AI. Okay, we're going to examine what's wrong with this. Just do a quick overview. I mean, a lot of you are professionals, you'll be familiar with these problems, but just for people who are not so expert on the situation, we just give a very quick overview of some of these problems. Okay. Now, Geoffrey Hinton says one of the reasons why he said what he said was a problem called adversarial attacks. Okay, so the leading way of doing AI has this major problem. Okay, look, this diagram illustrates a problem. Okay, the AI recognizes a panda. Okay, so it says, yeah, panda with certain amount of certainty, and then that's correct. But you can do something really strange. You can do what's called an adversarial attack. Now, there's this mask of bits is basically made from this gibbon picture, and you're basically altering each pixel ever so slightly to bias the neural network to try and get it to identify a gibbon. Okay, so you're hacking the network. Now you present. You change, basically you hack, subtly change the weights in the original network. Now you show the so-called artificial intelligence the same thing again. You show the artificial intelligence a panda. Now it says it's a gibbon. Crazy. Okay, so look, that looks exactly like the same panda as before, but you've tricked it into believing it's a gibbon. Now you can actually do the same thing with a kind of a stop sign becomes a go sign. This hack has actually been done in self-driving cars. Okay, so it's really quite disturbing, isn't it? So they're doing something not quite intelligent. We're just going to skim over the kind of these are kind of like critiques of the existing framework, because I think a lot of you be familiar. And self-driving cars, they have a habit of kind of crashing into parked emergency vehicles. So they're doing something really dumb. Okay. The kind of one kind of thing you shouldn't crash into is parked police cars, but the Teslas have a habit of crashing into parked police cars and emergency vehicles. So something's going on, and it's it's pretty disturbing and not quite right. And the other major problem is the kind of like there's a whole list of problems, but the other major one is the energy use. Okay, these existing AIs kind of driving all the kind of headlines is really they're using a lot of energy. Okay. And the amount of energy is increasing like about 10 times per year. It's unsustainable. So this idea of you need green AI, you need something really super energy efficient. We're going to show you what that is. Okay, the brain does something really super energy efficient. We're going to show you exactly what that is tonight. Okay, so now, okay, so someone who does very good critiques of the existing AI is a guy called Gary Marcus. So he's very good at criticizing the existing work. He doesn't actually offer any kind of solutions, but he's very good at giving a kind of a good overview of what's wrong. So if you look up his work, then that's a good place to kind of gain more information on what's wrong with the existing situation. But tonight we'll concentrate on actually the answers. Okay, we're actually going to show you exactly how to solve these problems. And we're going to, okay, internet connection is unstable. I had problems early on, so hopefully it doesn't cut out completely. Okay, so now we're going to basically just explain a bit more about what's wrong with the existing AI. So basically, this diagram is in 1,000 neural network, artificial intelligence, computation neuroscience, even theoretical neuroscience, even neuroscience books. Okay, this diagram is replicated again and again. You can see it's 100 times. Okay, it's an idea about how a neuron works. This is from 70 years ago. This is from the 50s. Okay. So, okay, this is kind of like kind of almost like a fictional neuron. Okay. And this is what's called a kind of artificial kind of neural network, a kind of model of that neuron. So let me explain. Okay, this is basically the dominant idea of what a neuron is, and it's completely mistaken, which we'll explain in a lot of detail. So these are the kind of like synapses on a neuron, and these are the kind of like, and these arrows just direct the synapses, the inputs into the dendrites, into the cell body. So that's the cell body. And it just does a kind of linear summation. It just adds the inputs up in a kind of linear way, then passes the sum into an activation function, which might be a kind of sigmoid, or what's most commonly used is what's called a rectified linear unit. We don't want to have to go into too many technicalities, but it's a really simple model of a neuron, which is really dominant in the world of kind of artificial intelligence. And it's completely mistaken. Okay. Which we'll go into minute detail. So these backpropagation networks use this model of the neuron, and it's basically replicated, kind of millions of times, lots of neurons in these models. This is a kind of simplification. So imagine each of these kind of circles is a neuron. So imagine that's the neuron from before, then these are all the inputs. The idea is basically you multiply the input with the synapse strength, and you add it together like in the last diagram. And of course, if you had a kind of lots of these neurons are kind of like being multiplied, what you have is a matrix. You have what's called linear algebra. Okay, you have vectors multiplied by vectors. So in the last diagram, what you have is a vector of inputs multiplied by the vector representing the synapses. You multiply the two, and then you sum. If you have lots of synapses, then you have rows of vectors, and you have a matrix. So to make this talk not as technical as it might be, basically that is a matrix. Okay, this is basically high school mathematics. This is linear algebra. So these are matrices, these are vectors. To cut a long story short, basically, this operation of multiplying a matrix with a vector is the basic underlying kind of calculation going on in modern artificial intelligence and these backpropagation neural networks, except that the vectors can involve hundreds, even thousands of numbers, and the matrices can be, hundreds, thousands of columns and rows across, okay, up and down. So we're talking huge numbers. We're talking synapses in terms of some of the new models, kind of 500 billion, 500 billion they're talking about. So we're talking like real kind of major calculations going on. Now the problem is, okay, this is a real major problem. Okay, the problem is that it takes loads and loads of energy. Okay, the situation with computers is that okay. The situation with computers is that basically, to do these calculations, okay, most of the energy goes into actually shuttling the data about. Okay, so I don't know why I keep losing myself on the thing. Okay, well anyway, look, what you have is basically multiplication units, and basically you need to get the data, the matrix data from memory into kind of your multiplication register. Now, the energy it takes to move the data around is actually 100 times, even 1,000 times the energy it takes to do the actual calculation. Okay, so the problem is these huge matrices. Okay, so I'm just going to mute everybody because I think it's interfering with the. Okay, so can everyone mute themselves? Okay, great. So everyone's muted themselves. Okay, now the problem is, okay, you've got these huge matrices, vast arrays of numbers, and they have to be shuttled from memory into these calculation registers in what's called GPUs or graphics processing units, with vast arrays of these multiplication kind of, to do multiplications fast. Now, the problem is the energy it takes to basically move the data from your RAM up your level 1, level 2, level 3 cache memory into your actual register. One calculation put it at the actual calculation is 1/1000th of the energy it takes to actually move the data around. Okay, the trouble with backpropagation, you move a lot of data around, and you move a lot of data around in many iterations. So, okay, one, you've got these huge matrices, but in order to learn anything, you have to iterate tens of thousands, even hundreds of thousands of times to learn stuff. So basically propagate signals forwards and backwards. To cut a long story short, you have to do loads and loads of these multiplications, and it takes loads of energy, and it's really inefficient. The brain is doing something with the energy contained in the banana that it takes these artificial neural networks to use the power of a power station to do the same thing, not as well. Okay, so that's the problem. Okay. So how do we solve the problem? The problem comes from biology. We're going to explain exactly what the solution looks like. Okay, so so matrices. Okay, major problem with existing neural networks is that they take loads of energy. The actual neurons are nothing like biological neurons, and basically we think the answer lies by going to biology and actually seeing how neurons actually work. And when we actually show the kind of like widest picture of neurons completely mistaken, then we have the keys to really creating this super efficient and super fast and super energy efficient AI. Okay, so look, that is basically the kind of workhorse neuron of the brain. It's called a pyramidal cell. Okay, so that's the main neuron in your cerebral cortex. These are different varieties of pyramidal cell, and it's basically it's about kind of like, we're talking about 1.5 millimeters from top to bottom. So very quite small, but very intricate. Now, what you see here is basically, this is not even a fraction of the neuron, because all you see here is basically the cell body, which is here. It's like a little pyramid. That's what I call pyramidal cells. And you're seeing the dendrites of the pyramidal cell. Okay, so these are the dendrites of the pyramidal cell. But the real extent of the pyramidal cell is in its axons. So let me show you a couple more diagrams. Okay, so it's very far removed from this, picture of a neuron. These are the dendrites, that's the axon. Now, real neurons have a really extensive, like, arborization of axons. Now, that's what you saw in the last diagram. That's basically the cell body there, where my cursor is. That is the dendrites. And that is the axons kind of like coursing through the local area of the neuron. Now, there's another example in the hippocampus. You see the same thing. That's the actual cell body and the dendrites. But it's the axons. You see how far spread this is. But even that is only a fraction of the extent of the axonal branching of these neurons. You see, here's another example. See, here's the, in black, in dark, that's the kind of dendrites and cell body. And the kind of lighter color is the axons. But in a kind of wider view, you see in this bottom part, that's the kind of, it's smaller, the dendrites and axon and cell bodies here, but now it's projected this other area called the striatum, which we'll talk a lot in the future, talk a lot about in the later on in this talk. Now you see, look, from here, it's projecting this other area, and it's kind of branching all over the place. But even that is a fraction of your typical pyramidal cell, because often these pyramidal cells will send a long fiber tract from one part of the cerebral cortex to a very distant part. So these are fiber tracts from brain scanning. But each of these fiber tracts is made of many fibers, but each of those fibers emanates, and it's a single fiber from a single pyramidal cell bunched together. But you can see it's coursing from one side of the brain to the other. And there's also the corpus callosum, the left brain to the right brain to the left brain, etc. And then when these long-range fiber tracks hit their target, they again ramify, they branch all over the place. So can you see, in physical terms, like real neurons are physically nothing like these kind of like abstractions in purely in terms of the physical appearance. But what's really important is the physiology and the dynamics of these neurons. Okay, so let me explain. Okay, so this modern understanding of a neuron has totally blown away that kind of 70-year-old picture from the 50s that has really kind of like which is really dominant in the world of AI and machine learning. Now, 21st century neuron, this kind of stuff has come to light really in the past 10 years, really, past 10, 15, 20 years. So all this is new information, practically most of it, or 99% of it is new information. Now, first, okay, it is now understood that neurons are dynamic. They are not static things. It's not, what you don't have is static neural networks. That neurons are constantly, especially the axons are constantly reconfiguring. They're constantly jiggling about. Okay, this is neurons in a petri dish. It doesn't move as fast as this, but they're constant in a state of motion. And at extreme end, in the part of the brain called the dentate gyrus, the hippocampus, new neurons form about 6,000 every day. And then these new neurons will form axons and dendrites. So point one is that real neural networks are dynamic. And we think that this dynamic aspect is intrinsic to the way they work. It's not kind of like, something like noise or something to be theorized out. It's inherent to what neurons are doing. Okay. Now, if you actually look at a neuron under a microscope, then the actual amount of movement of these axons it's glacial. But in aggregate, there's a lot of reconstructing, a lot of reconfiguring going on. And over time, basically, the entire brain regions will completely rewire themselves. Now, lower down the kind of sensory motor hierarchies, then things are more static. But as you go higher up the hierarchies to more cognitive memory areas, then you have this constant kind of like a reconfiguring of neurons going on, and especially with the axons. Point two, we'll go through this in fairly detail. My internet connection is unstable. Okay, fingers crossed, I just hope they don't cut out completely. Now there's this idea of dendritic patches. Okay, so dendritic patches are essentially, if you imagine what we had earlier, okay, this is the pyramidal cell. Okay, so up top to bottom is about 1.5 millimeters. Now these dendritic patches are essentially about 20 to 25 micrometers across. So, we're talking about tiny little patches. So when I'm jiggling about my cursor, we're talking about little patches about that size, and are scattered all over the apical and basal dendrites. And there's literally thousands of these little patches. And these little patches function autonomously. Okay. And they're kind of like, across a kind of 20, 25 micrometer distance. These little patches, they'll basically form little kind of modules that kind of like functional modules. One of the things they're doing is that they are doing a kind of cross-associative learning. Okay, so when they correlate, the correlation going across these little patches will tend to make these synapses strengthen. So what it's essentially doing, it's doing compositional learning. Okay, so basically when inputs synchronize in time to these little patches, then they'll form composite representations of those inputs. And then these inputs will tend to make these patches fire at the same time. These neurons, these little synapses will tend to be coactive because they're taking from inputs that tend to be active at the same time. So the learning associations, you've got little association learning modules. Okay. The other point about these little patches is they're not just doing compositional learning, which is a major problem actually with existing neural networks. These little patches are actually doing complex Boolean operators. So these tiny little patches are also doing kind of like, it was discovered just a couple of years ago that across a tiny little patch, you can do exclusive OR. So signal A comes in, signal A doesn't come in, then it fires. Signal B comes in, signal A doesn't come in, it fires. If signal A and B comes in, it doesn't fire. That's exclusive OR. Now, it's been known for years. About 10 years ago, it was discovered that neurons, dendrites do exclusive OR over a branch of a dendrite. But a couple of years ago, it's discovered it does exclusive OR over a patch. And all the other Boolean operators like and or not also are basically operators that happen over tiny little patches of of dendrites in a neuron. So you can see what it's essentially doing is something very different from the model of the neuron from 70 years ago. A fairly recent discovery, point 4, is that these neurons have local dendritic spikes. So it's not cell body spiking zone, all the kind of inputs go into the cell body and the kind of spiking zones in the cell body. What's now discovered is basically the dendrites of the pyramidal cell are saturated with literally thousands of spiking zones. Literally, these little patches can initiate spikes, and these spikes can happen spontaneously, all over the dendrite of a neuron. But what's really important that these spikes, these dendritic spikes, can actually drive a long-term potentiation, what's called spike time dependent plasticity. It just means that these modules are completely autonomous units. They can actually drive these dendritic spikes, local memory formation. Okay, so that's really interesting, isn't it? So a kind of modular neuron that's really, really complex. Okay, so we do dendritic spikes. Now what's, backward action potentials has been known for a very long time to happen in what's called Purkinje cells in the cerebellum. That's been known about 30 years ago. But we know now that they happen in all the main neuron types, workhorse neuron types of the brain in the spiny stellates of the stratum, but also importantly in pyramidal cells in the cerebral cortex. Now these backward action potentials have also been discovered to happen with the dendritic spikes. So we have this kind of almost like fractal kind of model of neuron where you have the kind of like a backward action potential. When the neuron fires, then there's a backward signal that travels backwards along the dendrites. Okay, you normally think the signal goes from the synapses to the cell body, but this backward action potential goes from the cell body back to the dendrite. But also the local spikes also generate backward action potentials. Okay, so it's not like wheels within wheels. And these backward action potentials can also can help drive long-term potentiation, spike time dependent plasticity. Now there's this very interesting feature of neurons which has been suspected to happen. Like 30 years ago, experiments were done whereby there was a kind of backward chaining effect. Okay, so what happened was that in the hippocampal neurons in a rabbit, this was known 30 years ago. Okay, over time, over many days and weeks, initially a chemical called protein kinase C involved in synapse memory formation would start to work at the beginning of the proximal section of the dendrite near the cell body. Then as days passed, this protein kinase C would translocate into a more distal region, kind of working itself backwards. Now, more recent findings have found basically that there's a kind of like a need for kind of like dendrites to be consolidated with these backward signals going backwards. And these backward action potentials are potentiated by signals in those dendrites to facilitate this backward chaining. And as it keeps backward chaining, if a signal arrives backwards and then there's no signal, then it kind of long-term depresses these ends which don't correlate with the kind of backward signal. So it's kind of like a backward chaining effect of it wasn't like a growing data structure going backwards in time, a kind of incremental effect, if you like. Okay, backward chaining. Now the other, which we didn't do in the last talk, which will basically, in recent decades, it's now discovered that neurons basically are stochastic. They are spontaneously active. And this is quite mainstream now. Entire books have been written about this. This activity, this noise, this spontaneous activity is not noise at all. It's actually intrinsic to how neurons function. If you take away this noise, basically, then the neurons don't work. So somehow this stochastic, probabilistic kind of like activity is somehow really vital to the functioning of what neurons are doing. Okay. Now, last point. Okay, just quickly go through the last point. Is there's a tremendous amount of temporal complexity that the neuron processes that we know now. So these little patches don't just detect kind of compositional correlates over a patch. It can also detect between two signals the temporal order of the arrival of those two signals. Okay, so that's interesting, isn't it? But also, what's also found is that like you have brain waves. Okay, you also have waves on these dendrites, little oscillations on the dendrites, and neurons inherently oscillate. Okay, and they also found that these little local dendritic oscillations will sometimes synchronize and sometimes desynchronize, and that this synchronization, this is cutting edge neuroscience, will then affect how the dendrites process information. So it's almost like a microcosm of a brain. You've got brain waves in a little neuron, like a fractal idea of a tiny little neuron being like an entire brain with like neuronal dendritic waves. Okay, so we have a radically new and different view of a neuron there, and it's basically going to blow away the existing kind of neural network models, because it would discuss the meaning of all these new findings, because it just basically gives us a kind of view of a neuron, which is basically the key to really, this massively energy efficient AI, but it's really the key to creating true artificial intelligence, which we'll show in due course as we go along in this talk. Okay, one of the implications of this new understanding of neurons is to show that a neuron is doing the most fundamental algorithm in all of AI. Now, why can I say this? Now, on the left, you see, this is the most used kind of textbook on artificial intelligence in the English-speaking world. 95% of all undergraduate, postgraduate, postdoc courses will use this textbook. Okay, Norvig and Russell's Artificial Intelligence, a Modern Approach. Now, okay, this most fundamental algorithm is in the kind of first 12 chapters is kind of repeated again and again about 6, 7, 8, 9 times in different guises. This basic algorithm basically describes a forward search into a space of possibilities, and then a kind of backward chaining from a goal state. So one example is basically game search. Okay, so you got pieces on a chessboard, and there's all the moves you can make going forwards. Then there's all the end games, and then the end games, and you backward chain from the end games. Then you forward search from the the kind of like board positions. If you can meet in the middle, you can meet, and then this position leads to that end game, checkmate. Then obviously that's your answer. Another example is robot situational calculus. Here's the robot. Here's where the robot needs to be. You backward chain to where the robot needs to be. Here's the robot, you forward chain to all the paths it can take, where the two intersect, there's your answer. And it is the same with logic, programming, propositional logic, first order logic, etc., proving propositions and stuff. So it's a basic idea that recurs again and again. And we think this most fundamental algorithm, okay, they express it in a diagram. We think that's the most fundamental algorithm. This is actually a diagram from the book of a divergence from a start state and a backward kind of emanating from a goal state, and the two intersect. We think that this is exactly what neurons are doing. Okay, so the axons are literally exploring into the space of possibilities, and you've got these dendrites kind of growing backwards, backward chaining from the neuron firing, and when the two meet, you form a synapse. Essentially what we're saying is that this most fundamental algorithm is actually happening at the level of a neuron. Okay, so that shows a kind of like a power in neurons which wasn't suspected before, doesn't it? It's essentially doing the most fundamental algorithm in AI. Now, there is a most kind of foundational idea in machine learning, okay, which is why is this the most foundational idea in machine learning? Because there's another very good book, okay, it's called The Master Algorithm by, the author is Pedro Domingos. He's a professor of machine learning at Washington State University. Now, in the first few chapters, he describes the most foundational idea in machine learning. He calls it tuple formation. So basically, you start with one tuple, you've got one factor, and what can you predict from that one factor? Well, not very much usually. But if you form two factors, you have a two tuple, and you can predict a little bit more. Then you form, like tri-tuples and stuff, etc. You kind of keep compositing factors together. And then you create disjunctions of conjunctions. So you have tuples, and you create OR cases. So, this and this and this, or this and this and this. And you keep doing that. That's the most foundational idea in machine learning, according to Pedro Domingos, a machine learning professor. But this is exactly what neurons are doing. They're forming these tuples across these kind of like little patches, and then they're joining up the tuples, and etc. You see, and then they're forming disjunctions of tuples over these kind of like dendritic branches, doing OR. So what we're saying is that basically the most foundational idea in machine learning and the most foundational idea in artificial intelligence is essentially what neurons are doing. Okay, so this is pretty important, I think, because it shows a kind of like, it gives neurons a kind of power which is really was not suspected before. There's a very important discussion happening in artificial intelligence today. It's basically the question of neurosymbolic. Okay, it is the question of it's essentially a question of you got the subsymbolic, which is visual pattern recognition. Then you have this thing called language processing, and then the symbolic processing, the higher level order processing. Now, there's a raging debate, and okay, the godfathers of machine learning, artificial intelligence, Jeffrey Hinton, Yann LeCun, Joshua Bengo, who actually Yann LeCun, Joshua Bengo were both Jeffrey Hinton's students. They're saying basically that backpropagation can do it all. They're saying basically the symbolic level can be handled with the continuous mathematics backpropagation level. Okay, they think they can subsume everything using backpropagation. We think they're absolutely wrong. Okay. Now, a person who agrees with me is a very influential voice, actually a very sensible guy. He wrote Keras, which is the Python interface to TensorFlow, which is Google's main kind of machine learning AI API. Now, Francois Chollet, okay, he says, okay, quote, neural networks are poorly suited at discrete problems that the people who are good enough at deep learning to realize its limitations are too invested in its success to say so. Smack. A lot of well-funded large-scale gradient descent projects get carried out as a way to generate bombastic press articles that misleadingly suggest that AI is perhaps a few years away. Many people have staked a lot on this illusion, but it's still an illusion. Kapow! I mean, really, what it's saying basically is that. Oh, sorry. Can we mute ourselves? Someone who's can we mute? Can everyone mute themselves? Okay. So really, it means that basically there is this kind of raging debate going on, and what Francois Chollet believes in, he works for Google, what many people believe in actually, DeepMind, people like Gary Marcus, people like Ben Goetzel, many leading names, they believe the solution is hybrid. They believe it should be a mix of kind of backpropagation, continuous networks with the symbolic processing aspect. Okay, we think there's a third way, which is actually suggested by this new idea of a neuron. Okay, it's essentially that this view of neurons doing combinatorial, essentially Boolean operations, suggests that neurons themselves are working in a way that's essentially symbolic or pseudo-symbolic, you see. So it's not the continuous will subsume the discrete, or the hybrid is the approach, having the continuous and the discrete. There's a way of actually solving the problem just using the discrete, and it's based on how neurons actually work. Okay, so I think that is the solution. Now, it doesn't sound so outlandish when you realize that when you consider transformers, which were initially used to process language, i.e. symbolic processing, are now being used to process images and sound, then that's the same idea essentially. What we're saying is just basically take out the back prop and just stick with the discrete symbolic, and that's your solution to the continuous versus discrete problem. And it's actually suggested there in neuroscience. And by going completely discrete and taking out the backpropagation and continuous, it means your machine learning, your artificial intelligence works really, really fast. Okay, that's one kind of upshot. Now, okay, the other point, okay, this is what neurons are also doing. Okay, it's essentially doing this what's called the Bayes formula. Now let me explain this. This is the Bayes formula. Okay, so the important thing about the Bayes formula is that it used to be called inverse probability. Now the important thing, just look at this diagram. Basically, basic kind of high school mathematics. That means probability of A given B. The essential aspect of the Bayes formula is essentially expresses A given B in terms of B given A, the inverse. Okay, that's what's inverting. Okay, so let me just stop this share so I can wave my arms about and wave my hands about to explain this. Okay, look, what it is this: the Bayes formula was originated by Thomas Bayes, and then all the stuff to do with Bayesian statistics was added on later by a guy called Pierre-Simon Laplace, the French Newton, the French Leibniz, like a very smart guy. Now, okay, the thing is, we think that the brain doesn't really do that complex, kind of Bayesian statistics. What it's essentially doing is that inverse aspect. Now, what's the fundamental inversion in the brain? It's time, isn't it? So these backward action potentials are essentially going backwards to going back in sense to the previous signal, to register the previous signal. Now, look, the problem is this: you're interested in A given B. Okay, you're interested in what the B's that predict A, but you don't know what the B's are. You can't track all the B's because you don't know what they are, and there could be an infinite number of all these B's. You can't track all of them. So the problem is intractable. What is tractable is if you're given A, what are the B's? In other words, okay, if a neuron fires, you don't track every single pattern of dendritic input that's happened in the past, you basically just track what the synapses that were active immediately before the synapse fired. So you're given A, okay, then what are the Bs? Which synapses were active just before the neuron fired? In which case you back propagate. You just keep a little short-term memory of all the synapses that were active, maybe 25 milliseconds or even a second before. Then you back propagate the signal, and then you register, you tag essentially with the backward action potential all those Bs. And if you strengthen those synapses, now you have basically those Bs predicting A. So now you got A given B in terms of B given A. We're saying basically that is essentially the Bayes equation in its absolute most simplest essence. And we're saying that's what neurons are doing. Okay, we explained that in order to show a complete unification of AI and machine learning, which we'll do at the end. Okay, so just for completeness, we had to explain that. Okay, next. Okay, so neurons are really powerful. So this idea of neuron as kind of a linear summation device, kind of sigmoid rectified linear unit activation function from 70 years ago, it's just completely history. It really is. I mean, it's just not the way real neurons work, and real neurons are so much more powerful. Okay. In the next section of the talk, we're going to explain, okay, something quite dramatic. Okay, we're going to explain. Okay, some of you here would have heard the last talk. Okay, in the last talk a few weeks ago, we explained how a neuron is like a gene. Okay, so go to my YouTube channel to hear the explanation, but it's quite fascinating. That gene and its gene regulatory networks, there's a symmetry. There's basically a perfect correspondence between a gene and its gene regulatory networks with a pyramidal cell. Okay, we explained that in the last talk. Now we're going to explain, okay, something really quite interesting. It's all part of the fractal brain theory. We're going to explain how a neuron is like an entire person. Okay, that sounds insane, doesn't it? It shows the power of neurons, what neurons are doing. We're going to show that the workings of a neuron, there's a correspondence with the workings of pyramidal cells, what they do, with what an entire person is doing. Okay, so this is very interesting because it leads to fractal artificial intelligence. The idea that you can create tiny little AIs that are little microcosms of entire organisms or entire people. Okay. This is how we explain it. Okay, this is how we explain it. Now, okay, these look like neurons, don't they? But they're actually artificial neurons. They're actually they're not artificial. They're artificially generated. They don't exist. They were generated using what's called diffusion limited aggregates and what's called Lindenmayer systems. So these neurons never existed. They were generated. The kind of Bible of dendrites, this came out in 2016. Okay, this is, if you want to learn stuff from up to 2016, then this is, if you read it cover to cover several times, you get a good idea what's happening with it's a telephone directory of a book. Well, one of the chapters in this amazing great book is it talks about neuron morphology, and they discuss how do we create neuron shapes. Okay, so what they do is they use two methods. Okay, they use what's called diffusion limited aggregates, and they use Lindenmayer systems. Now we think that it goes further than that. We think that yes, Lindenmayer systems and DLAs, diffusion limited aggregates, create these kind of neuron-like shapes. But we think it goes much further. We think that the way diffusion limited aggregates work and Lindenmayer systems, they reflect how neurons work, and they also reflect how people work. So if we can show how neurons are like Lindenmayer systems and diffusion limited aggregates, and then show how people are like Lindenmayer systems and diffusion limited aggregates, then we show how a neuron is like a person. So that's what we're going to do. Okay, that's what we will show you. Okay, so I'm going to explain for people. I mean, I know there's quite a few professionals here who are completely familiar with this kind of concept. We'll just explain for people less familiar what a Lindenmayer system is. Okay, Lindenmayer system basically generates these tree shapes. Okay, these trees don't exist like those neuronal trees you saw earlier. They're computer generated. Now here's more examples. These trees are basically, these fractal trees have been generated with a Lindenmayer system. Now Lindenmayer systems are essentially string substitution systems, which is a class of a very general class of things, including lambda calculus, including language production systems, including lots of kind of like aspects of formal mathematical systems and etc. So it's actually a very simple thing. It's actually basically, it's this idea of basically taking a a set of rules. These are the rules. So basically you have a little arrow. So A goes to A and B, or B goes to A. You apply the rules, the initial axioms, and you recursively apply the rules. By recursively applying the rules, you can generate tree structures. Okay, so that is basically the kind of Lindemeyer system that generates this little tree-like structure here. And this is the Lindemeyer system which generates this little fractal tree here. So I mean, what it means is basically there is, okay, to explain things in lay people's terms. The important thing is this little arrow. Okay, this is a mapping from a given state to generate the kind of like the implication state, if you like. If I see this, then I'll generate this other side, the right hand side of the arrow. Okay, so we think there's something equivalent to this in human brains. Okay. Now, that's easy to see if you've got this kind of system that generates little trees, and if neurons are little trees that grow out, okay, the dynamic of generating Lindemeyer systems is essentially capturing that little kind of neuron generating trees and exploring out. You just add another kind of like a kind of rule to maybe cut back on trees. So you branch out, you can actually withdraw and stuff. So essentially using Lindemeyer systems, then you will essentially create that kind of dynamic axonal remodeling using a Lindemeyer system. Okay, so that's how neurons like a Lindemeyer system. Okay, now diffusion limited aggregates. This is what a diffusion limited aggregate is. So I don't know. This is code from years ago I wrote. Okay, so look, this is what has been generated by the diffusion limited aggregate. Okay, so essentially you started with 4 squares, and can you see on the left-hand side of the diagram? So the 4 squares, if you like, are sticky. And you have a random walk of these black squares. Now there's random Brownian motion walk. And if one of these black squares sticks to one of these squares, it becomes sticky itself, and it takes on the color of that square. And if you keep doing it with these kind of like black squares randomly walking, this is just a little bit of code. Okay, so it will start. Okay, so basically it will grow backwards. Okay, it'll see from the initial 4 colored squares, this diffusion limited aggregate is growing backwards in time. Now, these used to be called slow grows because you run a computer overnight and you might get, if you're lucky, half this pattern the next day. But now with computers being so fast, you can generate this in a split second. I've kind of slowed this down so you can see the process in action. So that is a diffusion limited aggregate, okay? But this backward growth, backward chaining process is exactly what neurons are doing. So what we explained earlier about this backward chaining process is exactly what's happening with a dendrite. So diffusion limited aggregates don't just generate the shape of a dendrite, they reflect the actual dynamic of a dendrite growing backwards, backward chaining from the cell body. Okay, now we need to explain how is a person like a diffusion limited aggregate, and how is a person like a Lindemeyer system. Okay, so what we need to explain, okay, what the hell is going on? Has he got the wrong slide here? Has he basically put one of his holiday snaps or his kind of pet fish into his talk box? No, that's called a lamprey. Okay, that's a very primitive animal. Okay, lampreys were around even before dinosaurs. Okay, so that's such a primitive animal. It's like a fossil animal. Okay, like a coelacanth. Okay, now the thing about a lamprey, it has a basic circuit called a striatal circuit. It's a fundamental circuit that's in our brains as well. So a lamprey has a very primitive striatal circuit, and it's really, really important. It's really fundamental to how brains work, and a lamprey has a very primitive version of it. A shark brain has a more advanced version. When we get to tetrapods, we have basically a striatal circuit, which is pretty much identical to a human striatal circuit. So we have much more of the circuit, and everything we do, every movement we've made, every emotional reaction relies on the circuit. It's absolutely fundamental. Now, what is it doing? Okay, this striatal circuit relies on a chemical called dopamine, which is the chemical of addiction, etc., the chemical of what you lose in Parkinson's disease. So this circuit is really fundamental. What is it doing? Okay. It is so very fundamental. Okay, so this circuit called a striatum, what it's doing is processing time. Okay, so what it's doing, it's processing sequential behavior. But it's doing something. It's doing it in a very interesting way. Now that's a human stratum. So you can see it's huge, and it's in the middle of the brain. It's in a very strategic position. That's kind of like two parts in a human brain. In a lamprey, it's just a tiny little area, but in the human being, it's basically the same circuit that's been replicated again and again and again. Now, what we have is basically, that's a cerebral cortex, a kind of flattened sheet on both sides of your brain. That's a kind of like with the kind of areas drawn in. Now, the stratum interacts with the frontal parts of the frontal lobes, and it forms what's called closed loops. So the frontal lobes is basically, in this diagrams here, is the frontal lobes and also parts of the temporal cortex and parts of what's called the parietal cortex. The stratum will form closed loops. And these loops are closed because the stratum doesn't send signals out of the brain. It basically just works with the cerebral cortex. It doesn't do anything on its own. It has to work with the cerebral cortex, and it works with dopamine, this kind of chemical of addiction and chemical of motivation. Okay, just show you, these are kind of all the kind of brain areas in the prefrontal cortex. These are kind of schematic of the closed loops, and they consist of many millions of fibers in each patch of cortex. And these closed loops, basically, this is another schematic. Forget the cerebellum. I mean, cerebellum, we don't want to talk about tonight because just to save time. Okay, here's the striatum. And here's kind of the 6 layers of the cerebral cortex. Now, this is the closed loop of the stratum. Can you see it's like a loop going round and round and round? Now, what the stratum does with the cerebral cortex is it enables temporal sequence behavior and also thoughts and also sequence emotional processing happens. So it also modulates your emotion centers, your hypothalamus and your amygdala. And the dopamine neurons in turn form a loop of the stratum. So dopamine, stratum, cerebral cortex, they work as one kind of functional unit. Okay, if you activate if you lose your dopamine neurons, the stratum doesn't work. You're basically brain dead, and then your kind of like a cerebral cortex doesn't work. Okay, and if you take certain drugs like cocaine, caffeine, amphetamine, your dopamine neurons work more. Your stratum works more, and you think faster, you talk faster. Well, you know the story, don't you? Basically, your thoughts, your kind of like the machinery of your mind goes round and round in circles faster. Okay, so we've got to go into some more detail to really understand what the stratum is doing, because we think it's doing something so very important. We think it's doing something fundamental to creating true artificial intelligence. Okay, we have to go into some detail in the stratum. Now, this is another diagram of the main circuits. Okay, the main two of the main circuits involve what's called the direct pathway and the indirect pathway. Now, this diagram's hideous. I mean, I'll just stop the screen share and. So you have a hyperdirect pathway, which we'll ignore, just make things simple. You have a direct pathway, you have an indirect pathway. Okay, what does it do? The direct pathway, the direct pathway basically is like the go signal. So basically the direct pathway also outputs into the output zone of the kind of the stratum, but the indirect pathway is like the stop signal. Okay. So it's doing two fundamentally complementary things. And so if I can ask everyone to mute themselves, I could mute myself from here, but I can't seem to do it now. Okay, so if everyone can mute themselves and I can screen share, then okay. Okay, so you have the direct pathway, indirect pathway. The direct pathway is like the go signal that, things turn round and round, whereas the indirect pathway is the stop signal. Now, a certain kind of neuron type called the pyramidal tract neuron on the left, the left part of the diagram, will project to the indirect pathway stop signal. But another kind of neuron, which is more numerous and also more complex, called the intratelencephalic pyramidal cell, will project into the stratum to drive the direct pathway. Now, what's also really important is what's called streasones and matrix. Okay. So this is part of a rat brain. So this is, in a sense, a human brain. This will be a tiny patch relating to a kind of area of cerebral cortex, but this is the entire rat brain. So what we have here is the kind of the stratum is segregated into two areas. You can see the blue area; these are streasones, and the red area is what's called matrix. Okay, so you have streasones and matrix, and they do very different things. The importance of the streasome area is that they project into the dopamine neurons, okay, but the matrix projects into the kind of like I guess the output zone of the stratum, the globus pallidus internal, that go back into the cerebral cortex. Okay, so stop screen share for a bit. So what we have then, what you have is, okay, you got, okay, this sounds a bit complex, but let me explain. It all makes sense. You have indirect pathways and direct pathways, okay. And then you have streasomes and matrix, okay. Now, the two are intermingled, okay, but at the same time segregated. So what that means, you have basically, you have indirect pathways intersecting with the streasome and matrix pathways, but it means you have 4 permutations of pathways, and each of these 4 permutations are segregated. So it means that basically you've got streasomes and you've got matrix, but the streasomes will have their own indirect and direct pathways, which are segregated, okay, and the matrix will have their own indirect and direct pathways, which are segregated. Now, that sounds wildly complex, doesn't it? The important thing to understand is that the streasomes project into the matrix. They project into the dopamine neurons, and then the dopamine neurons project back into the stratum to enable it to work. Okay, to cut a long story short, okay, to strip out a lot of complexity, what it means that basically, okay, the matrix, which is really outputting back to the cerebral cortex. Okay, so basically this loop, which is driving a sequence of patterns, which it might be thoughts, it might be kind of motor actions, behavior, etc., or kind of movements of your mouth to produce speech. Okay, basically what you're doing is basically with the indirect direct pathway, you're saying basically repeat the loop until some condition is met, and you're saying basically you do this. You repeat this loop with working with the streasomes while the dopamine flows. Can you see? So while some condition, the dopamine will flow, enable this loop to repeat until some condition is met. Okay. Okay. How do you represent those conditions? Well, you represent those conditions using those Boolean operators we talked about earlier, XOR and not, disjunction, conjunction, and nor, etc. So basically, all the Boolean operators we spoke about earlier, we can kind of make an educated guess. This research hasn't been done yet because it's really the bleeding edge of neuroscience. All this research done with pyramidal cells in the cerebral cortex, we can extrapolate into the stellate cells of the stratum, because this is the new mode, new way of looking at neurons. It gives a kind of real power. But anyway, these pyramidal cells project into these stellate cells anyway. So you can take advantage of this kind of Boolean logic, can you see, to create these kind of condition code to drive these repeat until, I'm deliberately using this kind of language, kind of do while the dopamine flow loops, etc. What I'm saying is basically these most fundamental constructs of computer programming, i.e. while loops, repeat until, you can even do if then else switch, etc. I'm talking C, C++ here. It means basically what these circuits enable is essentially these kind of program flow constructs of computer programming. And we are saying that coupled with this Boolean logic that is found in these pyramidal cells, it enables us to do a very complex kind of way of well, essentially allows us to do the kind of algorithmic programming with the brain. It really solves the problem of what's called you got the neurosymbolic. It really solves the problem of the neuroalgorithmic, which is a very hot topic of research, but they're doing it using backpropagation. So we think that is the fundamental thing that the stratum is doing, based on the physiology, based on the kind of what we see, the connective patterns, etc. Now, how does that relate to the Lindenmayer systems? Because basically, what it means is basically is that the kind of mapping left-hand side to right-hand side mapping of string substitution systems is exactly what the stratum is doing. The stratum is taking from the cerebral cortex a set of conditions, okay, and then while the dopamine flows, it is then saying, given those conditions, I will map forwards in time to the next condition, etc. And so what it means is basically, these kind of like the left-hand side maps to the right-hand side, rules of Lindenmayer systems is essentially what the stratum these loops, with these inputs from the cerebral cortex into it, and then looping back to the cerebral cortex forwards in time, is what it's doing. So essentially, what the stratum is doing is creating trees forwards in time. It's basically the actions you can do going forwards in time, represented as a tree structure. Okay, okay. Now, why does the dopamine flow? Well, simply the dopamine flows from the hypothalamus. So it's like a cascade of dopamine, but initially flows from the wellspring of motivation, which is the hypothalamus. So just let me go back to the. Okay, so the reason why the dopamine flows in the first place is because, okay, this diagram, these are the emotion centers. And the ventral tegmental area is called a pathway of addiction. So basically, this is a key area at the top of the hierarchy that really gets the dopamine flowing. Okay, if you hijack the system with addictive drugs, and obviously you can make things like, for years in my life, I was kind of obsessed. Well, not obsessed, but kind of tobacco leaves rolled up in a tube became very meaningful for me in my life. I walked miles to get a pack of cigarettes, this completely addictive behavior. So these kind of substances which kind of hijack the ventral tegmental area, which kind of at the top of the hierarchy, making the dopamine flow, is actually normally activated by hypothalamus. Hypothalamus is essential, driving sexual behavior, thirst, hunger, warmth, etc. So that's why the dopamine flows. Which means that essentially at the top of the hierarchy, you do what you do until you can stop the dopamine flowing, until you satisfied your hunger, etc., until you got your cigarette or whatever. So essentially, what you're doing is you're doing the neural algorithmic based on actual neurophysiology. Okay, so basically, we think that is what this essential circuit that's been preserved from the lamprey onwards is doing. Okay. Now we need to explain how is a person like a diffusion limited aggregate. We discussed this earlier, didn't we? A diffusion limited aggregate. We just skip some of this stuff just because the time is getting on, and we just so this is quite easy to explain because we showed what is a diffusion limited aggregate earlier on. You basically have a central sticky point and you backward chain the structure. Now, back to the hypothalamus, what you have is this is easy to explain because it's basically psychology class 101. It's basic psychology. It's called, what you have is what's called unconditioned reinforcers, and these are hardwired into your brain. So this is things like orgasm, things like, I'm cold, then I became warm again, homeostasis, I was hungry, and then I'm not hungry. That's rewarding, isn't it? And these are unconditioned reinforcers. But what we have is conditioned reinforcers, that backward chain, and psychologists actually use this expression, backward chaining from these unconditioned reinforcers. So let me illustrate. As a baby, you know nothing about the world, but you know about your hunger, and you learn about things like, okay, this is a very contrived example. You are hungry. A little spoon. Okay, you start with your mother's breastfeed or whatever, or baby bottles, whatever. Something goes into your mouth, and then you realize, your hypothalamus says you're not hungry. Okay, so you have the sense of something going into your mouth, and then you learn. You have this kind of baby food. You see that the baby food comes from a jar from the kitchen cupboard. Then you go with your mother on errands to the supermarket, and this little jar of baby food comes from a supermarket. Then you learn you have to pay for it with money. Then you backward chain, and you have to backward chain to learn how to get money. You get the picture. It just means that from these basic unconditioned reinforcers that are hardwired into your hypothalamus and amygdala, you backward chain this kind of web of meaning, salience, affordance, and purpose in your brain. And it is essentially a diffusion limited aggregate. And then when your forward chain stratum behavior going forwards in time intersects this backward chain, then bingo, reward. So suppose I walk around randomly in the street and suddenly I see a £10 note on the pavement, okay? And then that's unexpected reward. Then the dopamine levels will rise, and then literally the connections between the pyramidal neurons in the cerebral cortex to the stratum will strengthen, literally. If the dopamine rises, you get strengthened synapse. And if you're disappointed, something you do becomes boring or frustrated or kind of painful, then exactly opposite. The dopamine levels will fall. Also, if you basically are disappointed in something and you don't get the reward, the dopamine levels fall, and then literally the synapse is broken. It's long-term depressed. Okay, so you see, So it means that basically you have this backward chain diffusion limited aggregate from your hypothalamus, and this forward chain of possibilities of things you do. And when the two intersect, basically that's what's rewarded. And so basically that's how you form this meaning, the why certain things are meaningful and certain things are purposeful and not. They derive from your hypothalamus. What it means is basically we have shown in very in a kind of broad coarse strokes how an entire human being is like a diffusion limited aggregate growing from the hypothalamus and amygdala, and then how we're also with these strato loops, how we're working like a Lindenmayer system, projecting forwards in time, growing these trees of behavior outwards in space. It means that there's a kind of essential symmetry between a neuron and an entire person. Now, we don't have time to explain this, but you can do the same analysis for all intermediate levels in the brain, i.e., kind of cortical patches, cortical columns, microcolumns, macrocolumns, etc., to form a totally fractal self-symmetry, self-similar architecture of the brain from the neuron right up to the entire person. And also, as I explained in the last talk, right down to the gene level, a gene working as a neuron. Okay, so that's in essence the idea of a fractal brain theory, a completely self-symmetrical architecture or self-similar architecture. Now, the significance of this for commercial ends is basically the same algorithm, the same brain, the same fractal brain can work in a microcontroller unit, with 500 kilobytes of memory and 16 bits or whatever, and the same algorithm can work in a smartphone, in a workstation, in a laptop, in a supercomputer, on the cloud, etc. It's a completely fractal architecture, and for commercial purposes, this has a lot of kind of like, it just means you can run it anywhere. The same algorithm can run basically in all these kind of formats because it's complete fractal. It's scale invariant. Okay, so how are we doing for time? Okay, so basically this new generation of kind of like a reinforcement learning algorithm, this new generation of essentially neural network is also coupled with a next generation of evolutionary algorithm, which so it explains quickly before we take just field one or two questions before we go to the rest of the talk. Now, okay, we've done a new kind of neural network. We've done a new kind of reinforcement learning, essentially. We've basically shown how these stratal circuits, which is the basis of reinforcement learning, how it works and how it does this algorithmic AI, which is a kind of leading edge, bleeding edge topic of discussion right now and research. Okay, this theory also leads to a new generation of evolutionary algorithm. Now, evolutionary algorithms are actually very widely used apparently in the real world. So evolutionary algorithms don't get much publicity, but apparently they're one of the most widely used optimization procedures in engineering and in various, people just use it. It's just a kind of unsung doesn't grab the headlines, but apparently it's used a lot. But the thing is, existing evolutionary algorithms really only use a fraction of the mechanisms of evolution that we know about now. Okay, so the work done back in the 80s, these mechanisms just weren't understood or weren't known back then. Okay, so now they are basically, we know more about it now. In a nutshell, the existing evolutionary algorithms, essentially what they're doing is basically, okay, with DNA, what you have is kind of coding regions of the DNA, which is roughly about 2 to 5% of DNA. Now, these coding regions actually code proteins, enzymes, structural proteins, etc. And these genetic algorithms involving, point mutation, crossing over, what they're doing is essentially concentrating on mutating these kind of coding regions that code proteins. What we know now is basically the so-called kind of junk DNA is where the real action is going on. This is the kind of regulatory mechanism. Actually, we discussed in the last talk these cis-regulatory modules, which we referred to the last video. But anyway, the new generation of evolutionary algorithm, we say, is really focused on, yes, mutating the coding regions, but it also mutates the non-coding regions using all these other mechanisms we discussed in the last talk, including retrotransposition, whole genome duplication, gene insertion, point mutation, of course, and then crossing over. So it's a whole battery of new mechanisms that basically were not known 30 years ago, 20, 30 years ago. for this new generation of evolutionary algorithm. Okay, so we're going to basically, in the next part of the talk, just show how this all unifies and how it solves some of the major problems with backpropagation. But we just take one or two questions if anyone has anything to ask now, and then we'll just plow on afterwards. So if anyone has any questions, I'll sip some coffee. If not, then we just plow on.
Hello, I'm having a little question. I already
Christoph,
had.
hello. I'm sorry I didn't reply to your email. I've been in
that's no problem.
hacker mode recently, so I've been mainly coding, very unsocial. Anyway, far away, Christoph.
No, I have the same question, but it also, I already had it the last webinar. But it's just like, is there a way to like incorporate the parallel universe theory in the fractal brain theory, or am I going too far?
Parallel universes. I mean, the parallel universes was this theory, Hugh Everett, basically to deal with this idea of solving the problem of quantum superposition and the measurement problem. So what he's saying is basically that the wave function doesn't really collapse. That basically all these superpositioned possibilities that all exist in parallel universes. Okay. Now, there's actually very direct correspondence between this brain theory and the idea of superposition, because what we have is basically this generative procedure which generates into an infinity of possibilities, but all superimposed. You can't work them out, because obviously you got a crazy combinatorial explosion, superimposed on top of one another in a space of possibilities. We don't actually believe in the kind of parallel worlds interpretation, but we believe that the quantum computers can be configured in such a way to explore all these parallel configurations at once. So I think, okay, I need to think about this more. I think there is a correspondence between this theory and its future implementation on quantum computers. And if there's a reduction of all quantum mechanics into qubits, because this entire theory is in terms of binary combinatorial codes and binary trees. If there is work on this kind of reduction of all quantum mechanics, there's Schrodinger's waves and there's Heisenberg's matrices, this idea that you can reduce all quantum mechanics into qubits, into a kind of a calculus of qubits, then I think future work could show there's a correspondence between his qubit work with binary combinatorial codes and binary trees, which can then provide a perfect mapping between this theory and future quantum computers, I believe.
Yeah. So
does that answer your question? Because it's very exciting, isn't it?
Yeah, no, really, it was really good answer. But so you do think the brain is a quantum computer then, after all?
I went to this consciousness conference. I sponsored to go in Tucson, the 20th anniversary, 2014. The famous consciousness conference, and actually met Penrose and Hameroff. Anyway, the quantum brain computer hypothesis didn't receive much support in that conference, because I think Hameroff and Penrose put too much on their microtubules. But I think really the brain, the way it works, really is taking advantage of quantum effects. It's not just microtubules; it's everything. It's the entire brain. So I think there is a kind of I think the brain is working like a quantum computer, and I think normal computers will not realize consciousness. But I can see, okay, this is a whole other talk. I can see a way that quantum computers can actually be conscious, but Christoph, that's a whole other talk. Okay, so I don't want to digress too much, but yes, I totally believe that the brain is a quantum computer.
I'm happy.
Okay, that's a future talk. I need to do some more work on this. Okay, is it another question?
All right.
any more questions, or else I'll crack on. Okay, so any more questions? I'll just drink more coffee. Okay, 3, 2, 1. Any more questions? Okay, we just continue. We're going to basically unify. Going to unify all the kind of methods of artificial intelligence now. Okay, So now we're going to basically show what the unifying algorithm is. We talked about evolution, didn't we? We think that. We think that basically all these processes, evolution, ontogenesis, axons, way they work, the way we describe it, and way we describe reinforcement learning and behavior, and also, like evolution and of thoughts, we think it's one algorithm. And we think the unifying algorithm is essentially differentiate, select, amplify. So let me explain. Okay, let me explain. Okay, oh, I didn't screen share. I need to do. I need to do. What's going on? What's going on? I need to. Oh, I closed it. I closed it. Sorry, just bear with me for 2 seconds. I need to just reopen this window. I don't need to share it. So pardon my clumsiness. Oh, I closed my share windows. Okay, sorry to. Just give me 10 seconds. Just let me open that window again. Okay, so let me just share that. So I need to cut this out. Okay, so let me just screen share this. Okay, so we think that basically there's a unifying kind of process. There's a single unifying process that can unify all the paradigms of machine learning and artificial intelligence. We're almost there. We're almost there, and it's basically this process of differentiate, select, amplify. We think that this is the universal process. Okay, so okay, let me explain. So you got like the theory of evolution, very important theory. Okay, so very important theory. Okay, so what is evolution? Okay, evolution is basically it is differentiate, select, amplify. So the folks in the Santa Fe Institute who study things in the abstract, so they consider evolution. Then what is evolution? It is this kind of idea that you're basically differentiating into all these kind of obviously variation in species and subspecies, and then you're selecting. Obviously, that's natural selection, and then you're amplifying. So those species or individuals who are selected breed more, and basically they're more represented genetically in the population. So evolution is the process of differentiate, select, amplify. But if you think about it, so is the process of ontogenesis. Okay, this very important process of ontogenesis is also differentiate, select, amplify. As we kind of like, as we kind of like from a fertilized egg to a body, then we're basically differentiating in space, and then certain kind of progenitor fields are amplified, get more blood vessels, bone, skin, etc. Certain progenitor fields are programmed to die. Okay, and so there's a process of differentiate, select, amplify going on in ontogenesis. When we think about neurons, okay, then what we described earlier with these dynamic axons, what is that process? Essentially, it is also differentiate, select, amplify. You're basically having axons differentiating physically into space. Okay, then they're being selected by certain criteria. That criteria is called long-term potentiation and what's called spike time dependent plasticity. And when they connect with dendrites at a certain time, at the right time with the right dendrite, then you form a synapse. The synapse will be strengthened. So literally, the synapse is amplified, and a connection is made between the axon and the dendrite in these little kind of functional modules we described earlier. So the workings of axons kind of branching into physical space is also differentiate, select, amplify. But as we described earlier, behavior and thought using the reinforcement learning circuit, the striatum, in its kind of Lindemeyer system sense, is also a process of differentiating into a space of possibilities, intersecting with this backward chain of salience and affordance and purpose and meaning from our hypothalamus. And those behaviors which intersect become literally physically amplified by dopamine. So behavior and thought and learning is also a process of differentiate, select, amplify. And then we can apply the same kind of thinking to the evolution of thoughts and behavior, differentiating, selecting, amplifying into a space of possibilities. Okay, now, okay, that's kind of metaphoric, isn't it? That's quite, that's not really science. You just kind of drawn all these different kind of ideas, and you use the expression differentiate, select, amplify to connect them all together. What we need is express this idea in a kind of formal mathematical language, and it becomes not just mere metaphor, it becomes symmetry, it becomes the same theory, it becomes a unified conception. So we now need to basically investigate the nature of science and mathematics, because we need to deviate from normal science, because we think there's an impediment which relates to actually backpropagation and use of normal differential equations and normal science with the continuous mathematics. And this new kind of science, this new kind of discrete description, which is necessary to create our unified theory. Okay, so we need to basically examine the nature of mathematics and science now to really get to the gist of this, because we need to make some very bold revisions that many people are suggesting is the case anyway. So this is part of a wider movement in science. Okay, let's quickly go through this. Chris, we need to explain the nature of science and mathematics, okay, and where it came from. Okay, so back in the late Renaissance, you had Johann Kepler and you had Tycho Brahe. Tycho Brahe had all the dots. Johann Kepler's big innovation was elliptical orbits. Okay, very simple. It was elliptical orbits, and basically you solved the data points, and basically you encapsulated. You basically explained the motions of the planets. It was elliptical orbits, not kind of circular orbits. And then came René Descartes with analytic geometry. Now you can describe the elliptical orbits in terms of mathematics, okay, in terms of these this algebra of analytic geometry. Then along comes Isaac Newton and Gottfried Leibniz, and they come up with differential calculus. Now you can see how the dots, how the elliptical orbits change in time. Now this, kind of like, dx, dy, that almost looks like backpropagation, doesn't it? It almost looks like the equations of most machine learning. Okay, this is the continuous mathematics of science. And this is the way most science has been done for the past 300 years. Okay, basically you can substitute joining the dots with corralling the dots with statistical science. But this is essentially the basic format using these kind of continuous equations, okay? Now, the trouble is that the continuous mathematics doesn't really do the discontinuous, it doesn't really do recursively nested structure, it doesn't really do fractals, it doesn't really do kind of discrete phenomena like we described earlier. So there's an alternative, which is discrete mathematics. Now, the thing about discrete mathematics is actually a superior version of mathematics. It's actually the deeper level of mathematics. People think it's like a poor cousin of mathematics. Okay, one of the towering achievements of the 20th century, intellectual achievements, up there with relativity and the formation of quantum mechanics, is Principia Mathematica. So to cut a long story short, what these two geniuses, Bertrand Russell with 2 Nobel Prizes and Alfred North Whitehead, what they did was they reduced all mathematics to what's called set theory. Okay, it's exactly what you learned in school, set theory, something quite elementary. This is from a Max Tegmark book. This is Max Tegmark book. He reduces all physics, all this kind of stuff of physics, relativity, quantum field theory, and he's showing basically all the mathematics of physics. Okay, yes, it reduces to discrete mathematics, set theory, Boolean algebra, etc. This is all discrete mathematics. But then he's saying it reduces to formal systems or formal axiomatic systems. Absolutely right. This is just, these are facts basically. It means that this kind of discrete mathematics, we think this is exactly what we need for theoretical neuroscience and also for artificial intelligence to progress. Now, it's going to seem so obvious because discrete mathematics is exactly what computer scientists and electrical engineers learn. The reason why there's such a domination of continuous mathematics in artificial intelligence and computational neuroscience is simply because many people come to it from a physics and also traditional engineering background. That's the reason why. But we think that's one of the impediments, that we make this switch into discrete mathematics, then everything makes sense. This is part of a wider movement. You can think of people like Stephen Wolfram, Brian Arthur, the complexity theorist, economist, talks about the coming of an algorithmic science to supersede the existing science. Okay. And also a case in point is, he died a few years ago, really smart guy, Eric H. Davidson was a Caltech professor. He did all the cis-regulatory regulation mechanisms on genes work. He is a really Nobel Prize deserving work. And his team realized that basically normal differential equations just weren't describing the genetic machinery very well. But he switched to discrete mathematics, Boolean logic, etc. Then everything made sense. We're saying that basically to really understand the brain and really understand, create artificial intelligence, you make the shift completely to discrete mathematics. Okay. Some of you might say linear algebra is discrete mathematics, but it's discrete mathematics using this continuous, the traditional mathematics. We're saying there's a purely discrete description of the brain. In the last talk, we won't go through this today because it takes a lot of time. In the last talk, we basically reduce everything in this diagram to discrete mathematics and binary trees. We show, okay, literally everything in the brain, cognitive science, practically everything. There's a kind of underlying binary tree, binary combinatorial code structure underlying it. Okay, of course, genes, okay, the 4 letters of the genetic alphabet is a digital code. We think it goes far deeper than that. We explain this kind of digital view of a neuron using, doing combinatorial processing, and neurons are binary trees. What we showed in the last talk and in my Fractal Brain Theory book in previous presentations, it takes a bit of time to explain, go through all this data. But we can show that all of it can be described in a discrete digital binary tree, binary combinatorial code language. Now, binary trees and binary combinatorial codes is the language of computer science. It is the language of information theory, essentially. But it's also the language of discrete mathematics, because all these formal axiomatic systems, all the relations of Boolean algebra, set theory, they're binary. All those kind of nested parentheses and kind of structures of logic, Boolean algebra, they're essentially binary trees. What we think is the answer is basically a merging of discrete mathematics with this special language, which is actually very commonly used in computer science. It's called, you can think of it as spatialized binary trees. So, okay, so we have this kind of, take my word for it, just go through previous YouTube videos and get my Fractal Brain Theory book. And we go through all this to describe this complete digitization of the genome and brain and mind, okay? But we have this language, we will recap and explain for people who are new to these talks. The language involves binary trees, okay? So let me explain this language. Okay, that is a binary tree. Essentially, every branch is binary going in 2 ways. So it's not that easy. That's what a binary tree is, okay? Now, the language involves this. Okay, so it's basically, okay, can you see that's a binary branch. I rotate the binary tree. I can then use a binary tree to represent these 4 squares. I can recursively keep subdividing, and I basically represented a grid. I represented a 2D space using a binary tree. Now, this actually, you can call it a quadrature filter. You can call it, a quad tree. It's actually used a lot in computer science. So the latest and greatest data video compression technology, H.265, and even H.266 uses a variant. It uses this scheme to subdivide 2D image planes. Okay, so it's very widely used. And you can also use these binary trees to represent sequences. So this is representing those spatial binary trees. You're taking a sequence, there's 8 sequenced in time. Okay, so basically I'm using it to represent time here. So that's called a balanced binary tree. I can do the same thing with like this. So that's exactly the same, but you can see this is an unbalanced binary tree. Now the thing is, I'm using binary trees here to sequence a set of spatial binary trees. Now the interesting thing is, this is exactly how the artificial intelligence programming language Lisp represents lists, by concatenating a head to a tail. So essentially it's a binary tree recursive procedure that creates structures exactly like this. Okay, that's theoretically quite satisfying. So these binary trees, these spatialized binary trees, these binary tree sequences are actually very fundamental structures. Okay, so okay, this is another way of drawing it. Okay, so basically this is the same binary tree but flattened out. Okay, so flattened out. Now, we need to introduce a kind of flexibility to this language. So we literally made it flexible. Now the last, the code from last talk, actually, I made the, can you see, like that binary tree is exactly equivalent to this binary tree. It's just drawn in OpenGL. I've made the lines thicker now, so you can actually see it, hopefully, on Zoom. Okay, so essentially what happens now is basically there's a flexibility. The trees, they can slide around recursively. So there's a slide factor, and they can slide around. So literally the language is flexible. You see that this is a binary tree. Now it can slide around, and it can also scale. It can also scale recursively, and in a kind of fractal. Now it's rotating. Okay, normal things don't rotate like that. It's just saying these what's called symmetry priors are kind of baked into the language of this binary tree language. So it handles these kind of basic affine transforms, a kind of subset of the affine transforms. You can see like that's a kind of honeypot on my table, and it's basically sampling the honeypot. Now it's distorting the image. So it's basically, so it's literally a flexible language. So it's taking what it's seeing through the camera on a smartphone, it's distorting it. But you can also take a template and you keep the the input from the camera steady, but you distort the template to match the input. So basically, it's almost like a flexible template that does more than a normal convolutional template, because it's recursively sliding and also scaling and also rotating. Okay, so the binary tree language, it's literally flexible. It can describe anything. It's literally like a universal language. And we think this language is exactly what you need to describe, basically to encode this theory of the brain and genome, and also to create true artificial intelligence. Okay, so very fundamental data structure. Okay, so we have our fundamental language, and we have, okay, now we need to explain the fundamental concept behind to unify everything we talked about. That fundamental concept is symmetry. Now we need to explain symmetry. Okay, now Symmetry AI is a very hot topic of research. Okay, so you've got people like Pedro Domingos is quite involved in this this area. A big name is Michael Bronstein here in London, also Max Welling of Qualcomm. And also DeepMind recently released a paper on symmetry. But the really interesting idea is symmetry working with symmetry breaking. We'll explain why. Just to quickly explain for people who are maybe unfamiliar and not have attended previous talks, we're just going to quickly explain what is symmetry in the broadest kind of layperson terms in order to understand symmetry breaking. Okay, so we're going to just explain what is symmetry in the most broadest applicable terms possible. Okay, so basically the idea of symmetry involves this idea of transformation and invariance. Okay, so with a given set of transformations, an aspect or a set of aspects stays invariant with respect to that given set of transformations. That's the most general way of defining it. So transformation, invariance, change, and immunity to change. That's the meaning of symmetry. So let me kind of explain. In the top of the diagram, you have basically the shape is transformed from a square to a hexagon to a circle to a star, but the color stays invariant. So that's the invariant aspect with respect to these given set of transformations. And then the bottom part, basically, you have a square, but the color changes. So now the invariant aspect is the square, but the color changes. Now you have these, what you learned in high school. This is the concept of symmetry that emerged during the Renaissance. This is what you learned in high school. So you take the square, you rotate it a certain number of degrees, 90 degrees, 180 degrees, and it appears the same. So you transform it with these given sort of transformations, rotations, and it appears to be the same. And you reflect in a mirror along these lines. Again, with these given set of transformations, the actual physical appearance of the square stays invariant. Now, this is slightly more complex. You take the basic shape and you basically translate it, you can rotate it, you can scale it, you can scale, rotate, and translate and reflect. But what stays invariant now is essentially the angles between the lines, proportions of the lines stay the same, even though it appears you've got different shapes. Now, the idea of self-symmetry or self-similarity, i.e. fractals, is the same idea where you take a basic shape, you make smaller copies of itself and you place it within itself recursively. And here's two more examples of fractals. Basically, you take the basic shape, you make smaller copies, you put it inside itself to make these fractal objects. Now, the binary trees we talked about earlier totally capture these aspects because the binary tree is essentially the most fundamental and most simple fractal there is, and the most important fractal, I'd say. Okay, so that's symmetry. Now, what is symmetry breaking? Okay, I'll explain what symmetry breaking is. So you have basically a kind of invariance under a given set of transformations. Symmetry breaking is when basically you have a set of transformations that leaves things no longer invariant. So basically, symmetry is broken. It's not the same shape anymore. You know, it's not the same color anymore. Basically, the invariant aspect has been kind of violated. Now symmetry is broken. That's what it means. All very technical, but let's explain in simple terms, in graphic terms, how we can understand this in very visual terms. Now, evolution, speciation is also a form of symmetry breaking. Now, okay, no, that's like a tree of life. You've all seen this in textbooks, haven't you? A kind of phylogenetic tree of life. So speciation, okay, is also a form of symmetry breaking. You have a symmetry class of members of the same species. Okay, but if you have a speciation, then symmetry is broken. Now, mathematicians writing books about symmetry will actually use a speciation as an example of symmetry breaking. So I'm not kind of like, misusing the language. It's a great way to explain symmetry breaking. Now, this is a very simplified tree of life. This is a more complex tree of life, but obviously the real tree of life is really, really complex. It involves every single, species that's ever happened since the beginning of life. So the real tree of life is really, really complex. But the real tree of life is a process of symmetry breaking. Okay, now another example of, sorry, that's the next part of the talk. Another example of symmetry breaking, which is the term symmetry breaking is also used, is ontogenesis is also a form of symmetry breaking. Okay, from a fertilized egg, if there wasn't symmetry breaking, then you would be basically a homogeneous spherical blob of cells. It's all exactly the same. Because there's symmetry breaking, because there's progenitor field formation and differentiation, you become, complex human forms, etc. So symmetry breaking is also part of ontogenesis as well as evolution. Now, the thing is, symmetry breaking is actually also how neurons work. Because we showed earlier how all these processes is differentiate, select, amplify. Now that's evolution, and evolution is symmetry breaking. This is a shortcut way of explaining things. Now, if we differentiate, then we break symmetry. Okay, so you got invariance, transformation, invariance. But if we differentiate, we are breaking symmetry. And if we recursively break symmetry, then we create these kind of like tree of life classificational structures. What we think is basically this idea of symmetry and symmetry breaking using binary trees is really the essence of essentially this theory, unified theory of brain, mind, and functional genomics and evolution that creates this really powerful new generation of AI. Would explain, okay, so everything in this theory, okay, is basically differentiate, select, amplify. That's the unifying concept from evolution to reinforcement learning circuits to neurons. Okay, differentiate, select, amplify, and it's symmetry breaking. It's recursive symmetry breaking. Now, what happens when you recursively symmetry break? We saw earlier, if you recursively symmetry break, like creating species, okay, you create these classificational hierarchies, don't you? The tree of life. This is very easy to visualize, isn't it? Because a tree of life is a structure of recursive symmetry breaking. But we're saying a lot of ontogenesis, reinforcement learning, and actions of neurons, everything happening in your brain, in your body, this process is in your minds is essentially recursive symmetry breaking, creating hierarchical classificational structures. And what we're saying is that your entire mind, every neuron, every reinforcement learning structure, this diffusion limited aggregate from your hypothalamus is one recursive process of recursive symmetry breaking. What's the upshot of this? The upshot is basically it solves three fundamental problems in artificial intelligence. It solves one, the problem of deep analogizing. Okay, huge problem. Okay, if everything is a process of recursive symmetry break, you're creating classificational hierarchies, which means deep symmetry involves finding two differentiated things and then finding the common base class. And there's your deep analogy, because everything exists in this theory of brain and mind in terms of hierarchical classificational structures. There's always a deep analogy to be found with any 2 points in representation space. Okay, that's quite abstract and theoretical, but it's a very important point of solving deep analogizing. Now, this is a really important point. Okay, I'm going to reveal how the brain is so fast. Okay, why is the brain so fast and so energy efficient? This is the reason why. If everything is recursive symmetry breaking, everything exists as a classificational structure. But if everything is classified, it means it's sorted. It means things can work really fast. Like the thing about pattern recognition, no matter how you slice it or dice it, pattern recognition is a search problem. You have a set of internal representations or words or tokens, and you have some object. The trick is to map what you're seeing or hearing to those internal representations. So you're searching a space, internal space, to match to the external input. So it's a search problem. In theoretical computer science, basically the most theoretical fast way to search is called binary chop search. Okay, if you have a hierarchical structure and the things are ordered in such a way, then that's theoretically the most fastest way you can search a given set of search items. Okay, theoretically, we are saying it's a very general rule. We are saying basically there's an idea in computer science also of making the data structure do the work. That you can have very fast CPUs and little memory, or you can have very slow CPUs and lots of memory. And like logarithmic tables, if you had everything in a table, then a lookup table, that's very fast. You just basically look up the result. You might have something that takes millions of iterations to calculate. But if you had a huge amount of memory, you just store all the answers in a lookup table, then to calculate an answer is like, it works in a flash. So this idea of basically, if you have loads of data structure and very slow processing elements, you can use the data structure to speed up and compensate for the slow processing elements. Now, what we have in the brain is lots and lots of data structure. We have billions of neurons, we have trillions of synapses, we have 850,000 miles of wiring in the brain. That's a lot of data structure. What we are saying is that data structure is completely organized as a single recursively differentiate, select, amplify, recursively symmetry breaking hierarchical classification structure. And that's the reason why the brains work so fast compared to existing artificial intelligence. Okay, and we see it with neurons. We see, that neurons are these dendrites, classificational dendrites. So you can actually prime certain dendrites to be searched over other dendrites. So you essentially have a classification structure that makes even a search within a neuron actually much faster than it would be if it was a complete mess. So okay, it's a simple idea. If things were sorted and organized in your life, everything in the right place, then things are much faster, aren't they? If things are a complete mess, you have to look through everything, then things are much slower. So it's a very simple principle in computer science, but also in life. If you sort things and classify things, then things work much faster. We think this is the key to understanding why the brain and this future generation of artificial intelligence will work much faster than what we have today. Now, okay, the third, before I talk about the nuts and bolts of commercializing these ideas, the third major point is this idea of looking at learning as a growth process, looking at learning, looking at the process of kind of forming new memories as a process of growth, and also as a process of recursive symmetry breaking. There's a massive dividend to this way of looking at things, because I'll show you now how it solves essentially all the problems of deep learning, all the things that deep learning needs to be. This new way of learning is essentially inherent to how it works. Okay, let me explain why. So all the things that deep learning needs to be, they're having trouble with transfer learning, like zero or few shot learning versus tens of thousands, even hundreds of thousands of iterations on your backpropagation network. And also on the fly learning, this is a major problem with existing kind of deep learning. That you have you have a kind of offline mode where you do all the learning. Then when you go into inference mode, you're basically, no learning occurs. So there's a demarcation between inference and learning. Now we don't work like that, do we? We work on the fly. We basically learn as we're inferring. Okay, this is a very important part of how brains work. We explained compositional learning earlier, how these compartments on dendrites are inherently doing compositional learning, and how this backward chaining effect was incremental and unsupervised learning, another major flaw and in existing artificial intelligence and reference frames, positional encoding, symmetry, inductive priors. Okay, so now we'll explain why this new way of looking at the brain essentially solves all these problems. So backpropagation needs to be all these things, but isn't. Okay, and there's no way you can seem to solve the problem of actually building these things into backpropagation algorithms. But we'll show now it's inherent to this new way of doing things. Look, there's a very important idea in neuroscience and also in brain science, and we think it's absolutely right. This idea is called predictive coding. It's also, in America, it's often called analysis by synthesis. If you like Carl Friston's work, he calls it active inference. Okay, what it is this: we think it's absolutely right. We think it's absolutely universal. We think it's happening at all fractal levels of the brain. It is the idea that basically what brains do, we basically predict. We're like a prediction machine. When we perceive things, we don't passively perceive things like a backpropagation neural network. We're always projecting an expectation and matching what we're perceiving to that expectation. So when we analyze things, we're synthesizing a kind of pattern to match what's incoming. We're predictive coding. We're always predicting what's about to come. We think this is fundamental. Now, by doing that, you are inherently, basically, you are doing transfer learning, because you're basically, you need to transfer the most symmetrical match to current circumstance. And basically, that's how you fundamentally work. Okay, so you fundamentally need to transfer. Now, okay, now, if you basically, so how brains work and how this theory works and how this new generation of AI works is inherently on the fly. You have to basically predict and analyze as you are basically interpreting the real world and as you're learning. Now suppose you basically have a perfect match. You have total invariance. So what you are, okay, so suppose a contrived example, you basically go to work and you go to the same train station, you sit in the same seat, and every journey, every morning exactly the same. It's completely invariant. There's nothing to learn. So basically you knew it already. So you got zero-shot learning. Okay, so you basically had to learn something, you knew it already, and you predicted, you made a perfect prediction. There's nothing to learn, zero-shot learning. Okay, so we think that's mostly the case, that we're quite energy efficient because we're always trying to predict things. Now, what do we learn? What we learn is the deviation from expectation. Okay, so it means that basically we say, this is what we expect, but then how is what we're expecting differed? That's the deviation. In data compression, this is called discrete postcode modulation. You basically, you then interpret that difference, and you basically interpret what is that difference, and then you compositionally learn that difference onto your expectation. So you necessarily incrementally have to add on to your existing model or construct. There is no catastrophic forgetting. You can't erase what you previously knew, because you basically, your new learning relies on building on top of what you previously knew. But we know that that's how we work. And this is how neurons work, this kind of backward chaining incremental process of learning. Which means then, if you have to add on to existing constructs, you need a way of positionally encoding that existing construct. If you basically, there was a deviation on your journey to work, in order to learn that new memory, you need to learn exactly where that deviation was. Okay, there's a strange person sitting in that seat opposite over there. You don't normally, that person, that's the unusual thing in my journey that's normally exactly the same every morning for the past 10 years. Okay. Now, in order to do that, you need to do positional encoding. Now, the transformers do this to some extent, but what we have is basically, this binary tree language to represent encoding, which we explained last talk, is how genes and actual brains represent things in space and time. But if you place some kind of deviation in a certain place but encoded, you also need sometimes to either rotate or scale or even reflect that thing. So let me give you another contrived example. I see a face, but how do I learn that face? I don't iterate 10,000 times to learn a new face. Basically, I find the best match in my existing database of that face. Then I learn the deviation from expectation. So like that new face looks like my brother, but maybe his eyebrows are slightly bigger. So I take my brother's eyebrows, and I scale it, and I maybe etc. You take an existing form, you take the deviation from expectation, then you compositionally learn incrementally, and you basically place, and then you scale, shift, rotate, you transform using the transforms we showed earlier in order to create a new construct. And we do this. This is a very general thing. So what we do for complex objects, what we do for the journey to work on your train, etc., right down to the neuron, we use the same process at all levels. What it means, basically, this way of doing things, predictive coding, kind of like learning the deviation from expectation and learning on the fly, you're necessarily having to do all the things with this new way of learning that backpropagation needs to be but can't do. So it's almost as if all the things that backpropagation needs to be is inherent, is intrinsic to how this new way of learning works. You see the beauty of it? And it's all deriving from this symmetry, recursive symmetry breaking process that is a kind of unifying process for neurons, for evolution, for reinforcement learning circuits, etc. Okay, so look, what we have then is essentially, we've gone through a lot, haven't we? We've gone through the most fundamental algorithm in artificial intelligence, machine learning. Okay, that's the beginning of the talk. We have basically gone through essentially Pedro Domingos's he talks about 5 tribes of machine learning. He calls them basically connectionists. We have a new connectionism based on how real neurons work. We have an improved evolutionary algorithms. We have a kind of way of doing symbolic processing, which is maps right down to the workings of neurons. And also we solved the problem of analogizing as one of his tribes, deep analogizing. We also inserted the Bayes formula early on in intrinsically how neurons work. But we also unified into our scheme using our analysis of the stratum, reinforcement learning. But we've also cracked the problem of symbolic, subsymbolic processing, how to reconcile the two. But we've also, in understanding the workings of the stratum, we've shown how the brain actually does the neural algorithmic. Okay, so all this combined into a single theory, really, a single concept. Okay, so that in a nutshell is the nature of the application of what you heard in the last talk. If you know, go to YouTube to see it if you didn't, this kind of unified theory of life and intelligence using the ideas of symmetry and discrete mathematics into the realm of artificial intelligence and machine learning. Now, just to finish off the talk, we are going to just to explain how would this become a startup? So how does it become a startup? How does this become product? Okay, so traditionally what you have is the theorist. You have academics working in academic labs like Geoffrey Hinton. Then you have students of his like Yann LeCun and Joshua Bengio. And eventually you have PhD students, and then these PhD students will create startups. So they're the programmers. And then you have, kind of like entrepreneurs who might then take these inventions and bring them, make them into companies. Okay, so what we think we need to do, we need to basically do all three. We need to be theorist, programmer, and executor, because really we don't have much time. The way that things are heading on the planet, I mean, we don't have time to go through all these levels, because seriously, in 10 years' time, we might not be here. Okay, so anyway, we need to do things as fast as possible. So how do we do it? Okay, the problem is, okay, there's something very problematic about the world of artificial intelligence. Okay, the problem is this. It is a secret. It's not a secret. It's kind of like an open secret that most AI companies, startups, don't really have a business model. What does that mean? It means they don't have a way of generating income. They don't have the way of basically making money. Okay, that's simple as that. What it is, the reason for this. Okay, one famous example is DeepMind. Okay, they basically they've been acqui-hired. This is a common pattern that these startups don't have a business model, and what they are bait for is basically to be bought up by these kind of big multinational companies like Facebook, like Google, etc. And DeepMind is probably the most famous example of this. The reason is for many reasons, but one of the reasons is that there is very little what's called B2C scope for artificial intelligence startups, which means business to consumer. So they're mainly business to business. So it's very hard to get a kind of cash flow going. So okay, let me give you an example. A recent article in Fortune magazine, discussed this difficulty of starting a business to consumer startup. And what they said was that okay, in a recent list of the top 50 AI startups in America, they basically said there were only 2 B2C startups in that list, and even that's doubtful. One of those startups was Duolingo, and you're thinking, do they really need? Okay, that's the language app. I've used it myself. Is AI necessary for this app to work? Maybe not, maybe not. The other one isn't even a B2C startup. So it's almost like the list doesn't have any true B2C startup. We think in the future there are opportunities for B2C, but we think it's mainly B2B. So most AI startups making money, they're basically serving existing companies. So one example in London is Tractable. They're basically using deep learning algorithms, backpropagation-based algorithms. And a lot of it's PyTorch, TensorFlow. They're using these existing APIs from companies like Google and Facebook. They're not even inviting their own AI. They're applying AI from these big companies to solve a specific problem. So Tractable solves the problem of car insurance, basically car insurance claims. So you got your wreckage, you point your camera, and basically your neural network evaluates the insurance claim. It doesn't do it perfectly, but does it well enough for insurance companies to use the technology. And they're a unicorn. They're worth over $1 billion in valuation. So it's like that. It's kind of specific niches like fraud detection for credit card companies. It's AI companies latching themselves to big corporations and solving some kind of business process, making it more efficient. We think there is a ginormous opportunity for this particular way of doing artificial intelligence, which we talked about. Okay, it's a huge opportunity, and it's been called the killer app of what's called industrial IoT. IoT is Internet of Things. So 5G, lots of kind of small computers in industry network to 5G to central servers. Okay, so this is what's called Industry 4.0. The kind of 5th industrial revolution, sensors everywhere, computers everywhere in factories connected. to basically analyze factories and workflow processes. So we think this is the niche, because the real criteria is energy efficiency. The software has to work on very small devices. We're talking kind of microcontroller units, often having 500K, not 500 megabytes or gigabytes, 500 kilobytes, and has to do something interesting with that. Now, there is TensorFlow Lite. There is basically people trying to apply deep learning backpropagation networks to this problem, but it's not very efficient. So all the things we talked about earlier, even with all these kind of tricks, sparsification, pruning, etc., to make these, these very inefficient nets efficient, it still doesn't quite do it. Now, Google had a kind of TensorFlow Lite, a kind of model working on 13 kilobytes to recognize, kind of certain words like wake up. Like, I don't think it works very well, because my smartphone, when I say, sometimes I'm rehearsing for the public talks, I say Hegel, the philosopher Hegel, and it thinks I'm saying, hey, Google. Okay, so this kind of, this kind of very small TensorFlow AI isn't quite doing it. What we need is basically a far more efficient way, which the ideas presented tonight will kind of create this kind of, from the theoretical talk you've heard tonight, in a kind of very, very kind of, in a much faster way. But there's a real market opportunity because Intel executives said that this was the killer app for industrial IoT, these kind of like very small computers that need a kind of super efficient algorithms to do basic pattern recognition. Now, you see this diagram here from a market research firm. What they've said is basically, okay, this reflects the killer app idea of anomaly detection, especially in IoT. So what Intel executive said was there's a thing called anomaly detection, which means basically it means that you have okay, so here you've got prescriptive maintenance and predictive maintenance. What it means is basically you have a ginormous factory. So that's like a ginormous machine, okay? And if the machine goes wrong or your factory line goes wrong, then it's very expensive to fix, because all your workers don't know what to do because the machine has stopped. So what you need to do, you need to do predictive maintenance. So basically this idea of anomaly detection. So it's very kind of straightforward to explain. Like when you're driving your car, things are going wrong when your car is making a funny sound, or if sometimes you smell a funny engine smell, or a funny sound, or a funny noise, or funny smoke's coming out of your exhaust that's a funny color. The engines. So the idea is basically this killer app kind of application is basically anomaly detection. You have loads of these little sensors all over your factory floor that kind of even smell, that can listen to machines, and also look at machines working and stuff, and you detect the anomalies. So what we think we are working on now is basically taking this algorithm and basically creating on essentially Android smartphones, talking to my laptops and the workstations, this anomaly detecting apparatus. Okay. So we think that basically this is how it begins. So we think that basically there is this idea called disruption from below, and this idea comes from a kind of academic. He died a few years ago, Clay M. Christensen, who came up with this idea of disruptive technology that comes from below. It's not always the case. I mean, but one famous example is the ARM chip. The ARM chip basically disrupted from below. Now, even the previous fastest supercomputer was using ARM chips. So you start from something like energy efficient, some low quality use criteria, kind of smartphones, not supercomputers, not data centers, and then you work your way up over the years. Then you basically tackle, and that's what ARM chip has done. Okay, so what I think is the kind of route for this kind of artificial intelligence is exactly. I didn't screen that I didn't screenshot that diagram. So basically, this diagram here is exactly this kind of starting from below and then kind of coming up to disrupt these higher order industries. We think this is exactly what you need to do to introduce this new kind of AI into the world. We can't really work on self-driving cars immediately. We can't really work on a challenge to Alexa or a kind of Siri immediately with very little resources. But what we can do is create this kind of like technology for anomaly detection And then later on, you branch off into smart homes, etc., and kind of burglar detection and that kind of stuff. Which is, there's people already doing it, but you do it in a far better, far more energy efficient way. So many people over the years have asked me this: what are you doing? What are you using? So what we're doing is we're doing a lot of C++ coding, okay, and we're basically doing a lot of Java coding. And there's a thing called Java Native Interface that allows your Java to talk to the C++ code. Now, it's kind of funny because, I'm not a professional coder. I did a lot of coding as a teenager in the 80s. But the funny thing is that the coding I was doing in the 80s, which was basically BASIC and assembler, because basically computers were so slow, you had to learn assembler to do anything that run at any kind of speed. So what I'm doing now is really, I'm working in a subset of Java that is really intersects with C++ and C. So really, I'm really doing C coding, really. I was kind of quite encouraged to hear Elon Musk in the Lex Friedman interview sing the praises of C versus C++, because I think it's absolutely right. When you do assembler programming, you literally, everything's a one-dimensional array. I find when I'm programming Java, actually working in terms of one-dimensional arrays to shuttle off into buffers into C++. So I'm really kind of writing a very low level of code, which is exactly what I was doing as a teenager, which is absolutely perfect for this kind of programming, microcontroller units and IoT programming. So the idea is to basically use my resources, which is essentially Android phones right now and Windows workstations, laptops, to create this basic application and make it as fast as possible in C, talking to a kind of Java superstructure that does all the networking code. And then what I need to get into, which I'm working on now, is full stack development, which has become much easier now than it was 10 years ago. So I learned, things like Java Enterprise Edition 20 years ago was a nightmare. But now there's frameworks which actually make it possible for someone to actually do full stack, something very simple in a matter of weeks, actually, these new frameworks. Okay, so that's what we're essentially at the stage now to basically create the first kind of minimum viable product. And in the future, obviously, you can build up in this kind of like this kind of pattern of disruption. So we start very simple. We start very basic stuff, even a little app on a mobile phone so people can play with it to actually see the basic pattern recognition working on your mobile phone CPU, not on the cloud, working very efficiently. And then just get things out there and basically develop it. And over time, basically, as you get resources, as you kind of like learn, as the technology gets better and better, you basically climb up and you pivot to all these different areas that, as you get more resources. But the main thing is that the purpose of this startup, I call it a startup at the end of time, the main purpose of the startup is essentially to create artificial intelligence. So you need to basically create the code, but as you're creating a code, you're not working in a kind of lab as an academic. You need to basically create the code and find utility, find use for it in the marketplace. And then, then the startup, I call it startup at the end of time, because I think it's going to create true AI and instigate the technological singularity. So it's really like the end of an epoch to a new epoch. Okay, so that's pretty ambitious. Okay, so basically, this startup at the end of time is meant to, yes, find markets and actually be able to generate revenue. But the ultimate aim of it is to create true artificial intelligence and eventually to create super artificial intelligence, and that's the aim. So there you have it. So we have a new generation of AI that unifies all the existing methods. That is really the kind of implication of the life intelligence theory that we spoke about in the last talk. And so I guess that's it. If anyone has any questions, we've gone for a very long time. My gosh, it's been 2 hours. That's quite a marathon sesh. That time passed really quickly. If anyone has any questions, I'm here.
I have a question. Me again.
Yeah, Chris, yes, go for it. Go for it.
No, just I'm curious. How far are you with your MVP to have something working?
I hoped to hack up some code for tonight, but I couldn't prepare for the talk and do both. Look, to make the thing work, I basically got the generator working. I can basically the basic learning algorithms working, but to turn that into a product. I just recently embarked on basically full stack development. Okay. at first I thought this is really hard, but I've been learning about this thing called it's called Spring and Spring Boot. It's built on top of Java, and I realized, oh my God, it's so easy. I mean, seriously, I mean, essentially you have the core algorithm. In order to make it useful, basically the core algorithm needs to basically be working, doing something, but what it's doing needs to be accessible on a mobile phone, and also needs to be accessible on on a any web browser. So the basic algorithm needs work. Okay, what I'm doing is I'm prototyping in Java, okay, because it's easy. Then I'm converting the Java code steadily into C code. Okay, now there is extra functionality to put into it. And basically, I've really, the coding has worked in conjunction with the theory. The theory has really come about during the coronavirus, actually. I've mentioned this in previous talks. Really, the work, it really kind of really clicked during these lockdowns, seriously clicked. So now I'm scrambling to find this unifying conception in my mind and then to convert that into code. So I'm hoping to basically, in terms of minimum viable product, in trying to make it something useful, I'm aiming before the end of this year.
Mm-hmm. Okay.
I mean, and make it. I got stuff. Obviously I can't give out code, but I got stuff I can play around with my smartphone. But I mean, I've just applied to download ImageNet. Okay, so they've not got back to me yet. If anyone has ImageNet, I mean, just send us a note. So I need to make benchmarks. I basically need to apply the algorithm to basically these standard benchmarks. So one thing to beat is that a recent startup generating excitement is they managed to get, it's not that impressive. They managed to get 76% accuracy on ImageNet using 500K neural network on TensorFlow Lite. So I think that is what we need to beat. And I think we can, because this technology is so much more compressed and so much, it's discrete, essentially. This idea of binarized neural networks, and also this idea of quantization pruning. It's almost like these ideas of making backpropagation neural networks faster, is these ideas taken to the absolute max. So I think that's one example of something I have to do now. But I think in terms of I need to get basically sympathetic solves that will allow the software into a kind of commercial context that I can use to basically get benchmarks and get kind of testimonials and appraisals and stuff. So I think we're talking not in terms of years, because I think basically this idea it is not a kind of theorist communicating with programmers and then programmers linking up with executors. It's happening in one head. So I'm saying there's a kind of level of integration and a level of execution which can happen in one mind, which is going to be much faster than a team. So what I'm aiming for is basically getting the basic prototype working before the end of this year, and hope to basically shove it out into some kind of working environment early next year. That's the kind of timescale we're looking at, Christoph.
Wow, really cool. Maybe last question.
Go for it. Yeah, go for it, man. I'll be here all night.
Are you gonna patent the algorithm, like in the States, or?
That's a really tricky one, because the thing about patents is that you have to basically reveal all your inner secrets. That's a problem. And if you've got a patent, you have to defend those patents. You don't have armies of patent lawyers. And the inventor of the TV, the inventor had the patent, spent his lifetime battling Sarnoff, who actually commercialized TV technology. And this guy who actually had the patent came out the loser. He basically, was nowhere. So I think patents are, I'm in two minds about patents, because I think patents are misused. I think especially the American patent system is really corrupted. It's really, it makes work for lawyers, but I think it's really misused by large multinational companies to suppress new ideas rather than protecting people with new ideas. So I think patents is a kind of, I think it's a two-edged sword. I think in a perfect world, there would be no patents. But I think, funny thing is, two of the people who follow my work, who have actually kind of supported my work a lot, is a patent lawyer in the European Patent Office and a former European patent lawyer. Someone working in the patent office, not patent lawyers. They actually examine patent examiners. Sorry, I should correct that. And one of the guys spends all day, every day examining machine learning patents. Okay, so I've spoken to both of these guys, and you know, if I was a startup, I'd have to pay these guys hundreds of dollars per hour to speak to these guys, but I could just, you know, I could just video call them, which is great. They impressed on me the idea, basically, how patent system works, but they impressed on me basically the trickiness that if you have a patent, it doesn't mean you're protected. There's all the hassle of protecting, like we mentioned. So I think there's actually the thing about new companies having patents and then, you know, somehow you're protected. I don't think it works. And also I think, okay, you need to promote the ideas. You need to promote, you know, spread the ideas. And I think there's lots to be said for open source. But I think ultimately you got to tread a fine line. I think you have to keep certain things secret. You obviously can't give out your code, you know, on GitHub. You know, it doesn't work like that, because there's nothing to stop other people from saying, "Oh, your code, my work. I'll patent all your ideas," kind of thing. So Christoph, I think I have to play a kind of like delicate game involving you know, trade secrets, involving kind of you know, people just keeping things non-disclosed, really, and maybe when a time comes when you have enough resources, you might have to apply for certain key patents in the future.
Yeah.
But in an ideal world, I think I'd like to see a world with no patents, where everyone just basically you know, is perfectly open source. But I can see now that basically when you're dealing with this kind of thing and there's money involved, I think there's lots of kind of like, you know what I'm saying, you have to be really careful about these kind of things, or else your invention becomes someone else's product and you become locked out of the market.